Yo Lemmy. Drop some science. It's a crazy situation. And about the speed of light and its wild fluctuation. Unforget what you heard. This ain't no constant race. Uncesium atoms, vibin', setting a brand new pace. Unwi token DNB boss number. A cosmic measure, uncertainties, the game. A scientific treasure. Have you ever sat down to watch a documentary, maybe about someone like Albert Einstein, and had a sudden mind-bending idea? That's what happened to me the other day. We're always told the speed of light is a constant, right? An unbreakable law of the universe. But what if it's not? What if, on an incredibly tiny scale, it fluctuates? I've come up with a little thought experiment, and I'm calling this fluctuation the DNB boss number. Let's dive into this. So, how do we measure things? How do we define a meter? We need a standard, something consistent. Imagine we decide to use atoms, like building blocks, to define our meter. Let's pick a big one, like caesium. A caesium atom has a diameter of around 0.52 nanometers. If you line up about 1.92 billion of these atoms, you'd get a line that's almost exactly 1 meter long. Seems simple enough, right? Well, here's where it gets tricky. The real world is messy. The size of an atom isn't a fixed, solid number. It's more of a fuzzy cloud of probability. When scientists observe cesium atoms, they don't always get the same measurement. The smallest diameter they've seen is about 0.49 nanometers. The largest is almost 0.69 nanometers. The average is somewhere in the middle, around 0.57 nanometers. This variability is a huge problem for our atomic ruler. If we try to build a meter by lining up cesium atoms, the length of our meter will change depending on the exact size of the atoms we happen to be using on that particular day. Let's do the math. If we use the smallest observed cesium atoms, it would take about 2.05 billion of them to make a meter. If we use the largest ones, it would only take about 1.46 billion. What does this mean for our meter stick? It means its actual length could be all over the place. If you built your meter using the biggest atoms, it would actually be longer than a standard meter. How much longer? About 1.2 meters. And if you used the smallest atoms, your meter would only be about 0.86 meters long. That's a massive range of uncertainty for what's supposed to be a fundamental unit of measurement. Now, let's connect this back to the speed of light. The speed of light is calculated as distance divided by time. If our measurement of distance to our meter's unreliable, then our calculation for the speed of light will also be unreliable. We're introducing a huge margin of error. Let's plug in the numbers. The accepted speed of light is about 300 million meters per second. But what if we measure it using our wobbly, cesium-based meter? If we're using the short meter made of the smallest atoms, the light would seem to travel faster to cover that meter. Our calculated speed would be around 361 million meters per second. That's a 20% increase. This gives us what I'm calling the high DNB boss number, plus 20%. On the other hand, if we use our long meter made of the biggest atoms, the light would seem slower. Our calculated speed would drop to about 257 million meters per second. That's a decrease of about 14%. And this gives us the low DNB boss number, minus 14%. So, according to this little thought experiment, depending on how we define our fundamental unit of length at the atomic level, our measurement of one of the universe's greatest constants could swing by a total of 34%. It makes you wonder, doesn't it? Are the constants of nature truly constant? Or does it all just depend on how we choose to measure them? It's a fascinating idea to ponder. What do you think? Is this just a fun mental puzzle? Or could there be something more to it? Let me know your thoughts down in the comments. Thanks for watching, and if you enjoy exploring wild ideas like this, make sure to subscribe for more. See you next time.